Okay, so the third speaker is Kevin Goldstein from WITS. He's telling us about ineffective black hole hair.
Okay, thank you. So let me give you the context of my talk. So I'm going to be talking about some very simply static, sterically symmetric black hole solutions in some effective higher order pure theory of gravity, so no matter. And in this context, generically at some length scale, one expects, if I start off with just Einstein gravity, generically at some length scale you expect high derivative corrections to be important. These corrections could play a role at the late stages of black hole evaporation, and if there were degrees of freedom that are introduced due to higher derivatives, perhaps they could play a role in entropy, and such solutions could provide new states for ADS-CFT. Good. So let me tell you, I'll give you the punchline at the beginning. So the good is that people have found solutions. Well, the good is that we found solutions which have a lower free energy at a fixed temperature than the Schwarzschild solution. The bad is that these are only small solutions. So small means they only exist at a small length scale. And the ugly is that because these are only small solutions and we're working in the context of some effective field theory, these are not acceptable solutions in the effective theory context. Okay. Good. So the Schwarzschild black hole is characterized only by its mass. I think there's only one solution, so that's why people say there's no hair. So at a classical level, there are no obvious degrees of freedom to account for this black hole entropy. That's why we came up with this term ineffective hair. So we're looking at high derivative terms that generically arise, and if there's more than one solution at a given mass, that would be some form of classical hair. But because this classical hair only applies to our highly curved solutions, they're not generically meaningful, so they should be discarded. So this is not valid hair. It's an extra solution, but it's not valid, and that's why I call it ineffective. Okay. Right. So let me now. So that's basically all I wanted to tell you about the solutions. That's the punchline. The rest is a lot of technical detail. So this is the setup we're looking at. So I have pure gravity. So here's the Einstein-Hilbert action, and then I have some at the next order. I have some corrections, and those are characterized by some length scale, which is the Planck scale, and then I'm going to drop a higher order term. So my higher order terms in this effective theory should be associated with the Planck scale divided by the curvature scale of my solution, and that'll be cubic. Okay. Here in my action, C is the Weil tensor, and R is the Ricci tensor squared. There's different ways you can parameterize this. You can add or subtract a Gauss-Bonnet term as you like. The Gauss-Bonnet term isn't going to affect the equation of motion. It will affect your the definition of the wall entropy. But here, the Gauss-Bonnet term is being added or subtracted, depending on how you want to look at it, so that the entropy you get matches what you would expect for the Schwarzschild situation. So once again, LC is a curvature scale associated with the space-time under consideration, and LP is the time scale. Right. So from this action, one can get some rather horrible-looking equation of motion, and there are two dimensionless numbers here, and there's one term associated with this Weil tensor squared part in the equation of motion, and there's one term associated with the Ricci tensor squared term. Good. So in GR, if you assume that we have a spherical vacuum, which is asymptotically flat, there's only one solution, that's the Schwarzschild solution. And people basically thought that this would go through at fourth order. But Lou Kirpin's Lou Perkins-Pappensteller showed in 2015 that if you assume static and asymptotically flat, that implies that the Ricci scalar is 0, but it doesn't necessarily imply that the Ricci tensor is 0. Okay, so there's the possibility for additional solutions in this concept where the Ricci tensor is not 0. If the Ricci tensor is 0, then the only solution is the Schwarzschild solution. And for non-zero Ricci tensor, there's a possibility for new non-Schwarzschild-like solutions. And so you'll notice that the terms proportional relating to beta involve either the Ricci scalar or derivatives of the Ricci scalar. So if the Ricci scalar has to be 0 because of a static and asymptotically flat ansatz, we don't need to worry about these terms. So we can take beta equals to 0 just because it's not going to, this ansatz means the Ricci scalar is 0, so we can neglect those equations of motion. That's part of the equation of motion. Good. So I'm considering this as some effective theory, which is valid at some length scale. If one insists on truncating and treating fourth order gravity as a theory in itself, it's not a great theory. So this alpha term, so alpha, if you don't want tachyons, alpha has to be positive, and even if alpha is positive, if you try quantize this, you're going to get ghosts. Okay, so this is not, if you insist on truncating this theory, it's not a good theory. I'm not insisting that, I'm just saying this is my effective theory at some length scale. Okay. Right. So these non-Schwarzschild black holes were found numerically by those authors that I mentioned, and they started off, they found that one can, you can't start at the horizon, and numerically you can't numerically integrate them numerically from the horizon, but you can do a kind of, you can find a, you can do a near horizon expansion, and then you can start off a small distance away from the horizon by setting boundary conditions, and you can integrate out, and one can integrate the metric, and you get some metric, and once you integrate this numerically, you find some black holes. Okay, so they found these solutions, and so this is their ansatz for a sporadic symmetric metric, and okay, so how you scale h for convenience. Let's see, so h here is in red, and when you set your boundary conditions in infinity, a priori you don't know how to scale h, how to scale your time, so that you scale to flat space with the speed of light is equal to 1, but you can do that after the fact. Okay, anyway, so these are the kind of solutions they found for various possibilities for R naught, which is the position of the horizon. Okay, good. And this seems to have died on me. Okay, so these, sorry. Right, so these non-Schwarzschild black holes were found numerically by those authors, and they integrated out from a near horizon solution. These equations are not really nice to integrate. They're called stiff equations, which basically means they're numerically unstable, and I'll mention the origin of this numerical instability later. But in order to get something which asymptotes to flat space, one needs to tune the initial conditions, and this is quite tedious and labor intensive. So the new thing that we did was we matched these near horizon solutions to an asymptotic expansion, and we found a new branch of solutions which have a richer behavior than the solutions found by those authors. Good. So just to return to the origin of the numerical instability, you can linearize the equation of motion for this fourth order gravity about flat space, and when you do that, you find some additional degrees of freedom. So there's the usual graviton, and then there's 2 additional degrees of freedom. There's a spin 0 massive mode, and there's a spin 2 massive mode, and the masses of these 2 modes are related to those dimensionless numbers that appeared in the Lagrangian, those two terms in the Lagrangian. So this was the term, this was the dimensionless number in front of the Ricci scalar squared, and that was the dimensionless number in front of the Weyl number squared. So because these are massive modes, because these are massive, they're going to give you some sort of Yukawa mode. And roughly speaking, in flat space, far away from my solution, I'm going to get something which looks like that. And so if the mass is, if I look at my positive mode, the solution is just going to blow up, and I'm never going to reach flat space. If I excite the negative mode, then this is going to die away, and I can asymptote to flat space. And this is the origin of the numeric. It's people say, I guess.
Because if you go from infinity by shooting, for example, you can never get this mode. I mean, if you just begin from infinity by.
Yeah, you could go. Well, then you have to try to shoot to get to the horizon, I guess.
Mm-hmm. But because of this decaying, I mean, it's hard to get. Is that a problem, or, I mean?
Okay. Well, maybe when I show the I'll show a solution. Okay. So, but if you try integrate out from the horizon, you have to tune the initial conditions so that you don't excite the positive mode.
Oh, it's the positive mode, which is the problem. I see.
So yeah, so you start at the horizon,
Mm-hmm.
and you need to tune your initial conditions so that you don't excite the positive mode,
Mm-hmm.
and get out to flat space. Okay, that's just what I said. So the positive mode blows up, so we need to tune the initial conditions to avoid it. You can also excite this mode by numerical errors, and that's what makes the numerical integration unstable. Anyway, so it remains to be seen if these solutions are stable or possibly metastable. Good. So just to show you the starting point, so we have some near-horizon expansion. So this is the ansatz biospherically symmetric metric, and one can expand it in some sort of Taylor-like series about the horizon. So one assumes the horizon is at some coordinate rho naught, and I've just scaled out this mass, the mass of the spin to Yukawa mode. One can scale it out of the equations, so I replaced R with rho. And anyway, so one can systematically plug in that expansion into the equation of motion, and you can solve it up to any order you like. It's convenient. Previous authors chose a parameter. So rho naught is the position of the horizon, and F1 is the coefficient of the first term of expansion for the GRR components of the metric. And it's convenient to make this parameterization, and you'll just have to take my word for it for the moment, but if you take this delta equals to 0, that corresponds to the Schwarzschild solution. This parameter C is related to trivial time rescaling. And when you solve these equations systematically, using the equation of motion, you only end up with two free parameters. So C is related to time rescaling, and the only free parameters we have are F1 and rho naught. You can solve for all the other parameters in terms of those parameters. Okay, so the near horizon expansion converges incredibly slowly. So this dotted line is the near horizon expansion. That black line is the numerical integration. And so these curves give you an idea. So that would be the order 9 near horizon expansion. And if you work, well, if Mathematica works really hard to give you the order 18 expansion, you don't get much further out from the horizon. Okay, so this is the length, the distance from the horizon in the units related to the Planck scale. Okay. Good. So that's the near horizon expansion. So from the near horizon expansion, we can find the temperature and the walled entropy. So the temperature is just going to be the periodicity of the Euclidean time circle, and it's not too difficult to take my ansatz and read off from the ansatz what the temperature is. And if we have walled entropy plus spherical symmetry, that's the expression for the walled entropy. And one finds that the walled entropy is going to be given by a quarter the area of the horizon plus a correction. And this correction is related to this delta parameter, which tells you the deviation from the Schwarzschild solution. Good. So that's what you can tell from the near horizon data. From the, if you want to do thermodynamics, you need to relate the temperature to the mass, which you can find from the asymptotic form of the metric. So, as I said, you can't numerically integrate from the horizon. You need to use the expansion near the horizon. And for a given horizon size, you need to successively tune the initial conditions so that you can integrate further out, further and further out with blowing up. So, sorry, the slide doesn't show very well, but you need to use some shooting method. So you run over some range of initial conditions, and you see over what range of conditions you can get further, and then you zoom in on closer and closer initial conditions, and you can integrate out further and further as you like. And it seems as if you can integrate out using this method as far as you like until your computer runs out of memory and strength. Okay. So okay, there's a better picture. So here I've taken some initial conditions, and my solution blows up over this range, and then I say, okay, then I have to take initial conditions in that range, and then I can successfully get something which looks more and more like it's asymptotic to flat space. This is a plot of the GRR component of the metric. Okay, so there's good numerical evidence that you can integrate out as far as you like by increasing numerical precision, but this is obviously tedious and time-consuming. So we decided it would be more convincing to match with some asymptotic expansion, or even if one could just match some asymptotic expansion with the near horizon data, you wouldn't have to do any numerics at all. So in order to do an asymptotic expansion, it was convenient to take a slightly different ansatz. So we just use A, which is equal to 1 over F, and we changed coordinates. We scaled out this mass of the spin 2 Yukawa mode, and we used two equations of motion. So one equation of motion, we took the trace of the equations of motion, and another one, it's almost like the trace, except we took the absolute value of G00. And then we expand the metric components about flat space and do some sort of systematic asymptotic expansion for the metric. Good. So the equation of motion one gets at first order. So these subscripts correspond to the various order of the metric. So at first order, we get some horrible, well, they're not too bad. They're linear, at least they're linear equations of motion. And playing around with those equations enough, one finds that you can rewrite them. One which is something which is easily integrable. And then the other one is there's some differential operator acting on this component A1, and it's a third order linear differential operator. Good, so the equation of motion at first order is that this third order differential operator in A1 is equal to 0, and we get that. And one can invert that differential operator, or in other words, you can find its kernel. And the kernel of that differential operator is that. And we can plug it in. And solving that, we get this component for the metric. So this is essentially what I said before. So we've got the usual thing. That's the 1 over r, which some number times 1 over r. That's what one has for the Schwarzschild case. And then you get a Yukawa mode with a positive mass, and a Yukawa mode with a negative mass, and then one gets an additional constant which just corresponds to rescaling time. So this, good, okay. So, and then plugging in at first order, we have these two components of the metric. And from this, in terms of these parameters you can read of the mass, and I get a second parameter, which I get lambda. So, and I'm going to discard this positive Yukawa mode because I'm not going to find something which matches asymptotically flat space. Good. So that's so reading off this parameter lambda. If I want to interpret that, I should look at the Newtonian potential in flat space. So the Newtonian potential is half of G00. So I have 1 minus the mass divided by R. So that's the usual Schwarzschild solution. And then I get this Yukawa mode, which is falling off as a Yukawa mode should. And then I can interpret this parameter lambda as the characterizing the strength of my Yukawa mode. My solution's characterized just by two parameters, the mass and the strength of the Yukawa mode.
Do you understand that big M has to be small because there's an epsilon in the definition, or you're only slightly perturbing around flat space? Or is
Okay.
it,
Well,
because
yeah, I mean,
it's
so-
pretty far, right? So
I've
you're
imagined-
allowed to expand there. Or
yeah,
is-
so I don't know exactly about the validity of this expansion. I guess one could be, but so I've started off with this ansatz, which says I'm near flat space. So
you
as
can only cover Schwarzschild, basically.
Sorry?
This is the factor of Schwarzschild, right?
so you could do this with Schwarzschild, and the series converges, even though epsilon is not necessarily small.
But here you are taking it.
So here I am assuming it's small. Good. I'll come a little bit back. I'll show you some evidence that this isn't totally crazy. Far away from the black hole, you can think of this just as a formal expansion. And far away from the black hole, one assumes that this whole term should be small. And this should be smaller, basically because it falls off like R. So it's not necessarily that epsilon's the small parameter. It's just that I'm keeping track of far away from my black hole. I'm keeping track. The epsilon's allowed me to keep track of the successive radial dependence of my solutions. Maybe is another way.
So it's roughly like R upon M, M R upon M in some units.
So it's roughly, so basically you've got either, okay, let me come back. I'll come back to a better expansion. Okay, good. So there's the New Horizon and the asymptotic solution both have two free parameters. So asymptotically, my free parameters are mass and the Yukawa mode coupling. And then the New Horizon, I have this F1, which I don't really have any intuition for, and then rho naught, which is the position of the horizon. So to match, to do a matching, we need to tune F1 for a given rho naught. And because to integrate out, I can only integrate out if I tune F1. So for a given rho naught, I only get one set. It seems like I only get one set of M and lambda. Okay. So continuing on, at nth order, my equation nth order, basically I get, once again, I get the same third order differential equation, but now instead of being equal to 0, it gives some source, and I can calculate the source from what I found at the lower order. So at each successive order, I can find the source for the next order by looking at what happened in the previous order. And this is also another equation one can integrate, and this Fn is something I can find from the previous order in perturbation theory. So these two equations one can solve. So this one, A, you can find by applying the inverse of this differential operator on J, or finding the Green's functions for that differential operator, which are not too difficult to do. So that's the expression one finds after one finds the Green's function. And then if you found A, you can plug it into there and integrate that equation to find an expression for H. So in principle, one can systematically solve these asymptotic equations up to any order. And that's what we did. So the integrals become increasingly difficult to do. We managed to solve it analytically up to third order, but beyond that, one could in principle solve it numerically, but we couldn't do that. We didn't take it. Okay, so I don't expect, I just want to give you some idea of, not that it's really important what the details are, but just to give you an idea of the level of complexity. This is the kind of source one finds at second order, and integrating, plugging that into those Green's functions, you find that expression for the metric.
So you don't get any log modes?
Sorry? Yeah, there are some logs.
Oh,
The logs appear, yeah. So you get logs and these exponential integrals.
there's the integral.
Yeah, so the EI is the exponential integral, and there's some logs. So but the logs actually die off, so they don't blow up. They actually because the logs also appear with the exponentials, which
So basically this goes to 0.
this goes to 0. Yeah.
Without having to put anything to 0.
Yeah. So maybe I'll do some plots, and then you can. Okay. So that's the second order solution. For the metric component, yeah, so it's basically exponentials, exponential integrals, and everything is all dying off. Even though so that exponential is killed by that exponential integral at large rho, etc. Good. Okay, I'll just skip over that. That's the second order solution. Good. So maybe it's just to give you an idea. You can read off. So you can expand that at large R. So the metric at large R. So here is the first term one would expect for the Schwarzschild solution, plus there's some Yukawa mode which dies off, and then the first correction, so we get exponentials and logs, exponentials, everything's dying off exponentially. Good. And basically if you set lambda equals 0, you can solve these equations and you'll get. So this is the 1 over the Schwarzschild, what you have for the Schwarzschild, and that's basically the series you get if you take 1 over 1 minus 2r to the minus 1 and expand. Okay, so this is really the expansion one should have for the metric, not the one that I wrote down. So it's some series in the mass in this Yukawa coupling, and that should be divided by the Planck length to the n, and then there are various components of the metric. And these components are quite small. So here, for example, is what one finds at second order. So the blue, this is just to give you an idea, the blue line is the Schwarzschild solution, and then one gets subleading corrections proportional to lambda, which are much smaller than the Schwarzschild solution, and this is a log plot. So on a log plot, these things become straight lines, so these subleading terms fall off exponentially, as opposed to the Schwarzschild solution, which falls off like 1 over r. Okay, so comparing so the black line is, okay, so let me start from here. So this is the horizon is over there. That little dotted line is my near horizon expansion. I trust my near horizon expansion for a little bit, and then I integrate out numerically, and I can try and match that with my asymptotic expansion. So you can see this is the third order asymptotic expansion, and that's the second order asymptotic expansion. So you can see that near the horizon, this asymptotic expansion is terrible. But rapidly it converges to the numerical solution very, very quickly. Good. So this asymptotic expansion is good, but it's only good some distance from the horizon. So that expansion that I wrote down actually breaks down near the horizon. It doesn't make sense. It's only when you're far away from the horizon that it's a reasonable expansion.
So are the two things overlapping a bit, or are the two analytics? Sometimes analytic expressions they overlap, even if they shouldn't. I mean, even if the expansions are done in version of the parameters.
So by
Your near horizon is valid until where?
Oh, okay. So the near horizon's good, say up to there. Not
Oh,
very.
I see, not more.
So there's no yeah. So
Sometimes they're overlapping, even if they shouldn't. I mean, we're
Yeah,
doing
that's-
structure, and when we do there with the 8 functions, and sometimes they overlap, almost perfectly, and
Actually,
Like
that's what
scattering calculations, they overlap, but there's a
yeah.
region of
That's
overlap.
that's what I was hoping.
I see.
but this is just something else. Is a question in different regional parameters. This shouldn't overlap, but I think for some reason it still does.
Oh,
But there
I
might be some region in parameter space where they do, but yeah, they don't. So one needs to join them by some region of numerical integration.
So how do you actually define horizon? Is it when this f is 0, right?
Yeah, that the horizon just comes from my metric answer.
Rho equal to 1?
Rho equals 0.
So, but then you're expanding those functions in epsilon, right? You want that whole thing to be 0? Or
So okay, no, I've got two expansions. So this is my near horizon expansion.
Oh, okay, yeah.
And there I'm expanding, so that's being expanded about the horizon at rho equals 0. And then my asymptotic expansion is about
Okay, so
flat
this is-
space.
This is one that
So
doesn't
these are
need-
two different expansions, and one has to match them. But one might have been optimistic, and I was optimistic, that there would be a region where they were both valid, and then you wouldn't have to do any numerics, but that wasn't the case. Okay. So, so now that we've got the near horizon and the asymptotic form, we can do thermodynamics. So to do near thermodynamics, we need the mass for a given temperature and entropy. So our method is to fix the boundary condition, fix the boundary using the near horizon solutions. We find F1 so that the numerical integration does not blow up. We integrate out numerically for a little bit, and then we match the asymptotic form of the metric with with what we get from the numerical integration. Okay, so let me just show you the results of what one finds when one looks at the thermodynamics. So this dotted line is, so this is a plot of temperature versus the radius of the black hole, or the position of the horizon, and we're working in units where the Yukawa mode has a mass of 1. So this is the Schwarzschild black hole, and as you know, as you make the black hole bigger, it gets colder. And so then these two branches are the non-Schwarzschild black holes, and this red line is the branch found by LPBS, and I called it the hot branch because it's always hotter for a given size of the black hole. It's always hotter than the Schwarzschild black hole. And then we found this cold branch, which for a given size of the black hole, it's always colder than the Schwarzschild black hole. And these black holes seem weird. Well, at least I guess strange if you've got used to black holes, is that as you make them bigger, they get hotter, which is, yeah.
What is that?
Sorry? So lambda is the coupling of the Yukawa mode. So if we look at the asymptotic form of the metric, let me find, sorry. Okay, good. So if you look at the asymptotic form of the metric, that's the Schwarzschild black hole, then this Yukawa mode comes with some coupling, some string. Lambda is a parameter of my solution that I have to extract. For a particular solution, I'll have a particular lambda. So I fix the position of, I fix the size of my, I fix rho naught, I fix the position of the horizon, and then I only get a nice asymptotically flat solution for particular choice of F1, and then I can match what I get with the asymptotic form of the metric, and that matching will give me a particular M, and it'll give me a particular lambda.
So once your solution lambda is given,
Yeah.
What is the peak coverage scale in the solution?
What? Oh, yeah. I'll get to that. That's the point. Well, that's the punchline. Good. Well, you can see. So this is basically okay. Well, to answer your question, this is basically in Planck units, roughly speaking. So these are highly curved solutions.
So all of the non-zero lambda equalize a coverage scale is Planck scale.
Yeah. Well, not quite, but the solutions which don't imply that are obviously sick.
There should be a solution where you basically, in the leading order, it's a short-term solution, but the higher derivative correction, use a part derivative correction.
Okay, so let me say, no, there don't seem to be solutions like that. So the Schwarzschild solution is always a solution to the higher derivative action. Okay, so
Or including higher derivative.
yeah, so the Schwarzschild solution is always a solution.
Exact solution.
Yeah. So but
Because then an R mu equal to 0.
because yeah, if you look at those equations, R mu equals to 0 is always a solution to the equations of motion. So this is always a solution, but for some parameters, one gets additional solutions. The question is whether those additional solutions make sense.
The answer solution is R mu is
R mu is non-zero. These are those additional solutions.
Then the leading on the Einstein equilibrium is balanced with a higher derivative. So that's why it gives a Planck scale coverage.
I don't understand why well, okay, so yeah, I don't think I understand exactly why you only seem to get Planck scale curvature solutions for these non-Schwarzschild solutions.
Well, because
Maybe it's because there's just some natural length scale in the problem, so
because your theory has only that.
Well, what
there's
you're saying is that it's happening because you are balancing zeroth order term with the first order.
okay, well there's something non-trivial which happens, let me show you something non-trivial which happens. Okay, good. So this is just a plot of the mass versus the size of the black hole. So so this is once again the Schwarzschild solution. As you make the Schwarzschild solution bigger, it gets more massive. Once again, these black holes don't behave exactly they behave in the opposite way. So here is this hot branch, and strangely, as you make it bigger, as the scale of the horizon becomes bigger, so as the scale of the horizon becomes bigger, the mass actually gets smaller. Okay? So as I try to make these black holes larger and larger, they get smaller, and in fact, at some length scale, the mass of the black hole becomes negative. Okay, so this is not the normal solution. This is not the situation. So I can write down a Schwarzschild black hole which has a negative mass, but doesn't have a horizon. So this is a black hole which has a horizon and a negative mass.
Oh, so it's not a naked singularity.
This is not a naked singularity. It has a horizon, but it has a negative mass. Okay.
And this is the ADM mass.
This is the ADM mass, yeah. So this is the mass that I'm reading off from the asymptotic. So I started off with an ansatz which explicitly has a horizon.
I see.
And I've integrated out, and I've compared that with an ADM mass. It has a negative mass. That's surprising. It's not necessarily pathological. It's, okay. And so this cold branch also, so as I make it smaller and smaller, the mass gets...
So what goes wrong with positive interference?
Okay, well, let me come to the next slide.
Okay.
Here, as I make the black hole smaller and smaller, it actually gets larger and larger. As you approach this point, as this curve starts to flatten out, the numerical integration becomes incredibly unstable. So I'm not actually sure what happens there. I suspect at some point the solution just stops. But I can't prove it. Okay, so here, unfortunately, the axes are not clear. So here is the important slide. So this is the plot of the temperature versus entropy. So this is the Schwarzschild solution, which we're familiar with, and so this is the normal behavior. So this is this hot branch which got smaller and smaller as we made it bigger and bigger. And also as you make it bigger and bigger, it gets hotter, but you also reach some point at which the entropy becomes negative. And as far as I'm concerned, that means that these black holes, this is just a pathological solution. So the walled entropy. So yeah, so the area is still positive. Obviously, you still a quarter A is still positive, but the walled entropy becomes negative. And for me, that means these are non-physical solutions.
No. I'm not. I don't know why.
Negative entropy.
Maybe no, but maybe the walled entropy doesn't apply in this limit. Maybe the walled.
Okay.
I don't have.
Or it could be it could be that since you're using higher derivative and somehow you're balancing the lowest order with the first order to get a non-trivial solution. So in principle, you should include even higher derivatives. Then maybe it's like an alternative series, and then
no,
the
sure,
whole
but just giving the theory. So I just have the theory, which somebody gives it to me, and if I would like for a solution which has negative entropy, so what? I don't know. But I think it's more like the walled entropy is not correct. If the solution has.
I see.
If the solution
interpretation of a walled entropy as an entropy is not.
Yeah, I think maybe the walled entropy is a good description for like some large scale or something. I don't know.
I don't know. Well, I'm not sure if it's, what's for sure is the walled entropy doesn't make sense. Whether either the walled entropy is the incorrect entropy or the solution is non-physical. One of those are the only two options.
Even the fact that as you throw in mass, it becomes smaller, right? That's already telling you something weird? Or?
Yeah, no, this is weird, definitely. So as I'm making it larger, the mass is decreasing. That's.
But the specific heat is still always negative.
Yes. Yeah. So the specific. Yeah.
So,
one interpretation of that is that if you truncate this theory, there are ghosts. So perhaps it's like you're kind of adding. So physically one can think of you're throwing ghosts into the black hole. So you're.
so that means the reason why entropy is also negative.
Yeah, so that's one interpretation of what's going on, is that I'm putting more and more ghosts, so which is why I would tend to lean towards thinking that these are non-physical solutions. Okay, but this was initially the slide which got me excited. So this is a plot of the free entropy, so the free energy versus temperature, and that's the Schwarzschild solution. So for this hot branch, the free entropy is larger. For this cold branch, the free entropy, the free energy is lower, which would suggest that the cold branch should be entropically favored, if not for the fact that they're highly curved solutions which don't make sense in the context of an effective field theory. Good. So just for a summary, is that we match near horizon to the asymptotic expansion for hydrogen black holes. We found new branch of solutions with interesting behavior. Unfortunately, these are only highly curved solutions. So if you really wanted to make, if these possibly could make sense, generically one has to consider higher derivatives, which becomes quite difficult. The asymptotics are kind of difficult to study. It might be better to use a different kind of series to study the asymptotics, and it might be interesting to try extend this to ADS or higher dimensions. Okay, thank you.
Questions for Kevin?
So what happened to the positive energy theory?
Let's see, so I'm not sure how that works for when one has high derivatives. Actually, I have to.
Oh.
I think these theorems are
Only for
derived at
Einstein
Einstein gravity, so I'd have to. I haven't looked at that closely.
It's very large.
Yeah, but it would be an interesting question to look at to understand what's going on with those theorems for high derivatives.
Is it clear that, or is it possible to check if you add the next high derivative term, whether the solutions just get small corrections or do they just vanish completely, or can they be just
Should be the big correction.
or some correction?
So what these people have done actually is they've thrown away the second order corrections because they said, okay, the second order corrections are ghosts, and they're just looking at the third order corrections. I think that in the spirit of effective field theory, one should just add the third order corrections and see what happens. I haven't done that.
But your solution is that the leading order is balanced with higher activity, right? That's why it's like that. Once
Yeah.
you have the higher order, next higher order,
Yeah.
all the three terms equal balanced.
Yeah. So
I'm not
optimistic. I'm not optimistic that I would get something nice, and it's a huge amount of work to start looking at
But
those third order
maybe
corrections.
they're just completely dying, or we think they're going to.
I think the leading order is balanced with the second term.
See, one might have.
All the balance is the enabling solution totally.
What I was hoping was that you could get sort of large solutions which would have a small higher derivative corrections.
Yeah, that's usually what it is.
But it seems like in this case you only get these small solutions at these high. You only get these highly curved
Suppose we
solutions.
have the higher derivative term, which does contribute even for the solution where harmony is zero.
Mm.
That usually can happen.
So,
Then it's a tiny.
if I think at very high, if you set R mu to 0, you just get the Schwarzschild solution. So R mu equals 0 will give you the Schwarzschild solution, even if you have however many higher derivative terms you like. Because basically, once you have R mu equals 0 and spherical symmetry, that's it. That's the Schwarzschild solution.
So are you saying that all the higher derivative terms disappear in the equation motion as has R mu equals 0?
Yeah. Well, I think
These ones certainly. These ones certainly.
I think
The ones
all
he has
that I've
added,
seen-
suddenly the equation of motion, those terms vanish.
I'm not sure about all the ones I've seen. Yeah, the Schwarzschild solution, the Schwarzschild black hole will be a solution. I don't know whether all possible high derivative corrections will have the Schwarzschild solution, but as far as I know, all theories I've seen, yes.
Okay, but suppose you don't restrict to the static solution. So
Okay,
you have
then-
some correction,
Okay, yeah,
and then higher derivative correction is a part of the correction.
sure, but that's very difficult.
I mean, it's a part of the correction.
Yeah, but even if it's so, if you try a stationary, even if I put in a stationary ansatz, so I have nonlinear higher order partial differential equations.
But it's a part of it.
Yeah, I mean, you could try some perturbation. I guess one could try some similar kind of perturbation about the curve solution set. Yeah, that might be an interesting thing to do.
Can I ask a question
Yeah.
related to ghosts? Suppose I did this exercise not in Lorentzian signature, but in Euclidean signature. So then there is no issue of ghosts or anything like that, right? Some equations you are solving. There is no horizon, but in
Yeah, but I imagine I think you'd probably still get you can think of it as, so there's another paper by LPPS, and they basically show how you can extract this length scale, so that you can extract the length scale at which these solutions appear by looking at the spectrum of a particular differential operator. That spectrum is related to the length scale, and they've looked at it not just in 4 dimensions, but in higher dimensions as well. And I think this has also been studied in AES as well. And it would appear as if so roughly speaking, this point at which these solutions appear and move away from the Schwarzschild solution is always at some length scale that's roughly fixed by the scale of your corrections. And I imagine that whether one looked, if one continued, I don't know, I imagine that if you continued this operator to Euclidean space, it would have the spectrum would have similar properties. But I don't know. Yeah.
still a bit confused related to Nora's question. So if you consider the actual alpha prime corrections of string theory,
Yeah.
I thought that it's actually via
Okay, so
via tensors that appear there. So you need conformal flatness to have all order solutions. Or am I?
okay, so
That's why
firstly,
it
this
is a
is
solution to all orders of alpha prime, right? But not d branes.
this is pure gravity. So this.
Yeah. So I mean, if thinking ahead, and if you want to consider the actual alpha prime corrections.
Yeah, I mean, once one, things might change completely if one included some
Other fields, sure.
other fields and some matter, and so we know cases where
But I mean, if you're choosing the high derivative corrections that will vanish when R being 0.
yeah.
Consider more general ones.
Well, these what I have. These are the most general.
We just take alpha prime corrections and put those in all the higher fields.
Yeah. Well, these are the most general ones at in 4 dimensions. At 4 dimensions, at second order, these are the most general ones. Modulo that you can add or subtract the Gauss-Bonnet term as you like, which is not going to affect the equation
and
of
that one
motion.
vanishes if you put them into 0.
Yeah, these equations of motion. So this is the most general equation of motion. It's at second order, and they vanish. They're solved by the Schwarzschild R mu equals 0.
It's related to the number of central charges you get, like E and C,
Yeah.
4 dimensions. I mean, the number I think is counting the same.
I'm not sure about higher. Yeah, in high dimensions, in the Gauss-Bonnet term is non-trivial. Yeah.
Other questions? Well, thank you, everyone.
I think the number is how many central terms are there?
So tomorrow we'll operate on the same schedule as